Hey students, Mr. Danahauer here. Today I want to explain how to draw Lewis structures. Sometimes Lewis structures can be difficult for people to understand, and we need that practice. Just like with anything that can be hard, the more we practice, the better we get. And so the purpose of this video is to give you a little more insight on how to draw molecular Lewis structures. Now, the ones that I'm going to show you are ones that we've already done in class. But I do know that some people struggled with some of those. And so these aren't going to be new, but I am going to walk through the different steps needed and show you how to draw those. So first of all, I've placed a few rules here on my screen, the rules for drawing molecular Lewis structures. And I want everybody just to remember that there's a difference between atomic Lewis structures, which are fairly simple, and that's when we just draw an atom like a carbon here, and then we place the valence electrons around carbon. It's 4 valence electrons. That's an atomic Lewis structure, and those aren't too hard to draw. The molecular Lewis structures are when we have more than one atom that are bonded together in a covalent molecule, and then we're trying to show in that molecule, are there any double bonds, any triple bonds, and where are the extra pairs of electrons that we call lone pairs? Okay, so the rules when we're drawing molecular Lewis structures: 1, the total number of valence electrons has to be correct, so I'll be counting that through all of these. 2, each atom needs 8 valence electrons, either shared in bonds with other atoms or lone pairs, those pairs that are by themselves. But the total for every atom in the molecule has to be 8. The exception for that is hydrogen. Hydrogen can have 2. It has one tiny little place to put electrons, and it only can take 2 electrons. And the last one is we need to have the correct central atom, which we'll talk about here. So I'm going to be using a couple of things. First of all, we'll be using this, where did it go? We'll be using this sheet here, the Molecular Lewis Structures Practice. Okay, so we'll walk through how to draw these. And then, of course, we're going to be using a periodic table. And so you're going to want to have that handy. That's a resource you need to be able to do this. And an important part of using this periodic table is making sure you know how to determine valence electrons. So real quick, let's just make sure we can do that. And remember, the way we count valence electrons is we start with the column that hydrogen is in. So that group, we start with that one, and all of those elements have 1 valence electron. Okay. In the second group, it's 2. So everybody in this group has 2 valence electrons. When we count, we skip this whole block in the middle. Those are called the transition metals, and sometimes we call that the D block on the periodic table. We skip that block of 10 elements, and then we keep counting. So this group has 3 valence electrons, 4, 5 in this group with nitrogen, 6 for the oxygen family, 7 for the halogens, that's fluorine, chlorine, bromine, and then 8 for the noble gases, the last column here, except for helium with 2. All right, so that's how we count the valence electrons, and that's super important for us to be able to determine the correct number of valence electrons, right? Like I said back here, we need to know the total number of valence electrons, and that's a critical piece of it, is looking at the periodic table and figuring that out. Okay, so we'll come back here, and we'll start with our first example, which is carbon tetrafluoride. The first thing that I want to do for these is I want to draw the atomic Lewis structures. And the way we do that is just draw, of course, the symbol here for carbon is C. And then I know that carbon has 4 valence electrons. If I go back to my periodic table, carbon is here. So if I count 1, 2, 3, 4. So hopefully we have that piece down, the valence electrons. I won't come back to that very often anymore. So 1, 2, 3, 4. Okay. Remember, when we draw atomic Lewis structures, it's okay to have single electrons by themselves. When we draw molecular Lewis structures, we will always have either bonds or pairs of electrons, and we'll never have singles. So we'll get to that. Fluorine, let's see, fluorine is in the second to last group, so it has 7 valence electrons. Okay, so the Lewis structure is going to look like this. So the reason we're drawing these for 2 reasons. 1 is to determine our total number of valence electrons in this molecule, and 2, so that we can determine the central atom. So how do we determine the central atom? It's always the one that has the most spots open for bonding, or we would say it has the most unpaired electrons. These single electrons right here are called unpaired. That means that there's a space to share another electron there with another element. So when we decide which one is the hub or the central atom, the one that's going to be in the middle that everything else is attached to, we want to choose the element that has the most unpaired electrons. Carbon has 4 unpaired electrons, and fluorine only has 1 unpaired electron. Since carbon has more spots to share, that's going to be the hub. So I'm going to just go ahead and start off here by putting, I'm going to erase those guys, carbon in the middle. And then this shows me the subscript here, the 4, F4, shows me that I have 4 fluorines. So I'm going to bond a fluorine. And almost all the time when we draw Lewis structures, we put things at right angles. So I start here. It doesn't really matter where you start. And at 90 degrees to that, I'm going to put another one. I have 4, so I'm just going to go all the way around. Okay. And there's my last one there. So I have carbon as my central atom, and I have my 4 fluorines all placed around it. Now, why did I put a line between each one of those? Because I know that in this molecule right here in CF4, that means when I put all that together, it means they're all bonded together as one unit. And so I know carbon tetrafluoride, this molecule, has a bond from the central atom to all the fluorines. That's what's holding them together. So I can automatically assume that there's at least one covalent bond between every carbon and fluorine there. Okay, so I have my basic structure. Now there's multiple steps to get to the correct structure, right? For this one, this is a good start. Now we need to figure out what's the total number of valence electrons here. So carbon, we have 1 carbon, and there's 4 valence electrons on that one. Fluorine, every fluorine has 7, but we have 4 of those. So 7 times 4 is going to give us 28, all right? And plus the 4 there, total number of valence electrons is 32. Remember back to my rules, we have to have the correct number of valence electrons. We can't add any or take any away. So the correct number for this molecule is 32 based on the number that carbon has and the number that fluorine has. All right. Now the next step is we have to put all of those electrons somewhere on the molecule. Now we already have some of them placed because when we drew our structure, we had some already bonded there, right? So if I look here, this, do red here, okay, this represents 2 valence electrons. So I already have 2, 4, 6, 8. I already have 8 total. Now, some people like to subtract that. So they'll come over here and they'll do -8, get their total down there. I do it a little differently, and I just start counting my bonds, and I keep counting until I get to 32. So you can do it either way. Either way is fine. You just need to make sure you end up with 32 electrons altogether. So I'm going to go ahead and start counting. So I've got 2, 4, 6, 8, and now I'm going to continue to place them in pairs around every atom that's not full until I fill it up. So I'm at 8, okay, 10, 12, 14. Let me just make a note. I'm at 14. Now look, I filled up fluorine, right? Fluorine can have 8. So if we count up how many it has here, it has 2 in that bond, and then 4, 6, 8 total. So that's why I stopped putting electrons around that fluorine, because once you get to 8, it's full and we can't put any more on there. So I was at 14. I'm going to keep going and move on to another atom that's not full. 16, 18, 20. That one's full. 22, 24, 26. That one's full. 28, 30, 32. Now, I just finished, right? I counted my bonds first, got to 8, and then I kept going until I got to 32, placing those pairs on. So now I have all 32 of the electrons properly placed in this molecule. That is my second to last step. The very last step here is I need to see, are all of the atoms full? Do they all have 8 valence electrons? Or remember, we call it having a full octet. That's why these things bond together, so that they can share electrons with each other and get full. That's why they bond. So we want to see, does everybody have a full octet? Or do we need to make some adjustments to this Lewis structure so that everybody does? If everybody's full, then we're done. If somebody's not full, then we need to make one more change. So let's do a quick count. I'll change my color here again, purple. So when I count these, all right, I'm going to count a bond as a pair of electrons being owned by whichever thing it's attached to. So basically, like in a bond, those two electrons are gonna count for both of the atoms that it's bonded to. So let me show you what I mean, okay? Let's count this fluorine first. I'm gonna circle everything that it owns. So it has 2, 4, 6, and then that bond is 8. So that fluorine is full, all right? It has 8 electrons total. Some of them are shared, and some of them are just on the fluorine. So that one's done. Let's keep going around, checking for 8. 2, 4, 6, 8, that one's full. 2, 4, 6, 8, that one's full. 2, 4, 6, 8, that one's full. Check, all of those are good. What about carbon? We got to check all of them. So I'll use a different color here. I'm running low on colors. All right, let's do green. Okay, so I'm going to circle carbon. What does carbon have attached to it? It has 4 bonds. Every bond is going to count for 2 electrons to each atom that it's bonded to. So carbon has 2, 4, 6, 8. So the carbon's full. So this is a good Lewis structure because it follows our rules. Let me go back to the rules again. First, we need to have the correct central atom. It was carbon because that had the least amount of unpaired electrons, the most unpaired electrons, okay? So that was our hub. We put that in the middle. Then the total number of valence electrons has to be correct. Let's go back real quick and count and make sure that we have the correct total number of valence electrons. I'm kind of cleaning up my mess here because I'm using all kinds of colors. So if I just start counting, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 32 electrons. So that is true, and that's good. We need to make sure we have the right number. That's what we were expecting to have. The reason I went back and counted that is because it's a good check, right? Maybe I made a mistake whenever I was drawing this or erased something I shouldn't have, and I go back at the end and I check and I'm like, oh, I only have 30 electrons. There must be I need to fix it, right? So always go back in and check on your final structure for the whole molecule. Do you have the right number? And then lastly, that last rule is to make sure that each atom has 8 valence electrons. And we don't have any hydrogens here, so we won't worry about that. All of these should have 8, and we just went through and counted that they all have 8, so that's a good structure. All right. Okay, let's go on to another one here. So I want to see, I do have hydrogen, so that's good. All right, SO3, sulfur trioxide. We'll learn how to write some of these name some of these molecules eventually. Not quite yet. Okay, so again, first step, let's draw the atomic Lewis structures so we can figure out which one is going to be the central atom. Sulfur has 6 valence electrons, so it looks like this. Each oxygen has 6 valence electrons, so it looks like this. Now, we have a problem because both of these atoms have the same number of unpaired electrons. Sulfur has 2, right? And oxygen has 2, which makes sense because they both have 6 valence electrons. So how do we know which one goes in the middle? There's another trick for that, and that would be looking at the formula. And usually 90% of the time, in a molecular compound, a covalent compound, we put the central atom first in the formula. So because sulfur comes first here, I'm going to put it as a central atom. So I'm going to write it here. Okay? Now I know the oxygens, the 3 oxygens, there's 3 because it says O3, are going to be bonded to that hub, to sulfur as the hub. And I can put those oxygens wherever I want at 90-degree angles with 1 bond to start. Okay? So, again, it doesn't matter where you put. You could have 1 up top, 1 to the side, 1 of the side's empty. It doesn't matter, but you got to have 3 of them bonded to that sulfur, all right? Now, we've got our central atom. We have our structure started. Now we need to find the total number of valence electrons. Sulfur has 6. Each oxygen has 6. So 3. We have 3 of those. 3 times 6 is 18, right? Plus 6 is 24. So we got 24 valence electrons. I did that right, didn't I? Yeah, okay. Sometimes I make mistakes on these. So now we need to continue placing those on. Pick a different color here for that. And I'm going to, again, if you like to count up the 3 bonds, so there's 6 electrons already used there, and subtract that and then count, you can do it that way. I just start counting from 0 and count up to 24. So there's already 2, 4, 6. And now let's keep filling up each of the atoms until they're full, and we'll move on to the next one. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, I got to stop. Okay, because 24 is the max. I can't put more on there. Can't put less either, but I can't put more on there. So that's where I am. Now, next step, does everybody have a full octet? So if we look here, okay, let me change my color again. If we look here, oxygen, let's count oxygen. It has 2, 4, 6, 8, so it's good. This one's the same. 2, 4, 6, 8, it's good. This one's the same. It's good. What about sulfur? Now, okay, so different color. Bear with me on my colors. I just think it helps to see the different colors. Let's see sulfur. Sulfur has 2, 4, 6. It is not full. That means this is not the right structure. So what do we do if we don't have a full atom in our structure? And the answer is we need one of the atoms that is full to share a pair of electrons with the one that's not full. Now, all the oxygens are full, so we can take a pair of electrons off of any of those oxygens we want to. It doesn't matter which one. And instead of it being only on the oxygen, it's going to be shared between that oxygen and the sulfur. So here's what that might look like. I might just come over here and cross that pair off and make a double bond. Now I'm going to go ahead and erase it. Okay. So when I did that, now let's count sulfur. Now sulfur has 2, 4, 6, 8 electrons. So our sulfur is good. But wait, we just changed the oxygen. So did we mess up the oxygen when we did that? No, we didn't. Look at this. If we count the oxygen now, it has 2, 4, 6, 8. So the oxygen was still good. It just doesn't get to take that whole pair by itself. All right. It is actually, oops, sorry about that. It's actually sharing that pair instead of just hogging it to itself. So this is a good structure. It has one double bond. And again, that double bond could have been with any of the oxygens. It doesn't matter which one. We would have picked one and just made it into a double bond. Okay. Okay, let's keep going. So S2 is the next one. Get my pen colors right here. Now, if you ever have try again, Dana Howard, a molecule that only has 2 atoms in it, like S2 or whatever, there is no central atom. Okay, and another example of that is already on here, down here with HI, hydroiodic acid. All right, that only has 2 things, one hydrogen and one iodine. So there is no hub because we just have 2 things that are bonded together. So if you have a molecule that only has 2 atoms in it, and no more, only 2, then we don't need to do the central atom thing. We can just say, well, I know sulfur, come on, write for me, is bonded to sulfur. That's where we're going to start. And you can draw the atomic Lewis structure if you want, but it's not really necessary. We do need to make sure we know how many valence electrons there are, right? So each sulfur has 6 valence electrons, and there's 2 sulfurs, so 6 times 2 equals 12 valence electrons. Okay, all right. We're done with the central atom because that didn't apply here. And we need to put on 12 valence electrons. So I'm going to start counting 2, 4, 6, 8, 10, 12. Got to stop because I got to the number that I have here. So next step, let's check and see if everybody has a full octet, if everybody has 8 valence electrons. All right. So the first one I'll look at is here. And I've got 2, 4, 6, 8 in the bond, so that one's good. And then let's come over to my other one there. All right, and use purple for this one. And I have 2, 4, 6, only 6. So we're not full. We're not done. This is not the correct structure we need to do a little more here. Because this guy's not full, I'm going to take a pair of electrons from the one that is full, cross it off, and make it share. Make a double bond there. So this is the correct Lewis structure for that S2 or sulfur molecule, right? A couple of things to point out. Again, it doesn't matter where these extra electrons are. Like I could take those, they could be up here. That doesn't really matter. I could take these and they could be up here. That doesn't really matter. What does matter is you didn't do anything like this, that we have one there and one there, or like one there and one there. That's not okay. We can't have we can't have individual electrons. When molecules come together, when atoms come together and form covalent bonds, all of the electrons are going to end up being paired up. Okay, they're always in pairs. And you'll learn about why that is when you learn about electron configurations in chemistry class. But for our purposes, just remember that when you're finished drawing your Lewis structures for molecules, you will never ever have individual, like loner electrons. They are always going to be either a pair that's in a bond, represented by a line, or a pair that's what we call a lone pair, just the pair of electrons hanging out on an atom. Okay? So again, we've got our total of 12 valence electrons. Everybody has a full octet. Central atom is not an issue here. So we'll move on to our next one. PCl3. So we're going to start moving a little faster here. Okay. If you have questions, just go ahead and put them in the chat. I'm just kidding. There's no chat because this is a video. All right. Phosphorus has 5. So 1, 2, 3, 4, 5. All right. Chlorine has 7. 7. So who's going to be the central atom here? Well, remember, I told you phosphorus comes first, so that's a good clue. And phosphorus has 3 unpaired electrons. Chlorine only has 1. So phosphorus is our hub, P. All right. And we're going to go ahead and bond Cl3. By the way, some people get this confused and they think that it's carbon and 3 iodines like this. That is not what we're looking at here. And it is hard to tell. If you type something on, the computer, a capital I, and a lowercase l look very similar to each other. It's hard to tell. So this is chlorine. And how would you know that? I guess just from experience. And we probably should make a note on there to let you know that that's the case, since you're kind of rookies at Lewis structures here. So I'm going to put my 3 chlorines, okay, around the phosphorus, bonded once to start. Here's a caution. Some people get double and triple bond happy. Just like, let's put extra bonds on there right away. No. That's the last step, okay? The very last thing you should do to your Lewis structure, besides checking to make sure it's right, but that last step should be to make double and triple bonds. And only if somebody in the molecule is not full. That's the only time we do it. Okay, total number of valence electrons. Phosphorus has 5, plus chlorine is 3, right? Cl3 times 7. That's 21, plus 5 gives us 26. Now, one thing you'll notice, all of our valence electron numbers have been even numbers. 32, 24, we had 12 here, okay? And now we're at 26. If you get an odd number of valence electrons for a molecular Lewis structure, you did something wrong. Very, very rarely do we have an odd number. That's only if we have a free radical, something weird that we're not going to learn about. But remember, every element was going to have 8 valence electrons. So that means that by default, we have to have an even number, right, total, so that the molecule can actually come together in the right way. So it's always going to be an even number. If you get an odd number, then you need to check your answer because you probably did something wrong. So here we go. We're going to go up to 26, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where does the last pair go? I got to get to 26. There's a spot right here on phosphorus, 26. All right, so we got all of our valence electrons on there. If we count up, is everybody full? All right, this chlorine has 8, 2, 4, 6, 8. It's good. This one looks the same. It's good. This one looks good. Phosphorus, I keep doing my colors here because it's kind of fun. All right, even though it's a little obnoxious. Okay, and then we've got 2, 4, 6, 8 for phosphorus. So this is a good Lewis structure because I've got 26 valence electrons. Everybody has a full outer shell. They have 8 valence electrons, and I've got the right central atom. So this guy's good. Okay, so no double bonds on this one, right? We don't need to do any more bonds. Some people just really like to put extra bonds on there, and that usually messes us up. Don't need to do that here because everybody's full. All right. Okay. Hydroiodic acid is our next one. HI. It's a friendly molecule. Okay. So again, we only have 2 elements bonded together, so we do not need to worry about a central atom. We can just put H and I together. All right. Now, total number of valence electrons, H is 1, I is 7. We add them together, we get 8. Again, even number, right? Now, here's where hydrogen comes into play. When you have hydrogen, you are done. Hydrogen cannot have anything else. It has a bond to it, and that's it. So you look at hydrogen and you say, sorry, dude, you're done. We're not doing anything else with you. Leave it alone. No double bonds, no triple bonds, no extra electrons, nothing. Once it's bonded, it's done. It can only have 2 electrons, okay? Now, where do the rest go? They go around the iodine, the I. So let's see here. Goes red, blah. Okay, so we're going to get to 8. We've got 2, 4, 6, 8. If we count them up, iodine's full, right? 2, 4, 6, 8. So it's good. And then my hydrogen's good because it has a bond, and a bond counts for 2. So it's good, right? That structure is done. Again, no double bonds, no triple bonds, none of that. Okay. Let's go on to Si2. Again, we're kind of picking up the pace here. So silicone. This is silicone dioxide, often found in a sand like quartz. Quartz is often a component of sand, which is mostly silicone dioxide. Silicone has 4 valence electrons, also used to make glass, by the way. The way they make glass is kind of fascinating. Anyway, oxygen has 2, 4, and 6 there. So which one's our central atom? Again, silicone comes first. And then also it has 1, 2, 3, 4 unpaired electrons. It can share 4 times. That's a good indicator that it's going to be our central atom. Oxygen only has 2 spots that can share 2 lone or single electrons. And so we're going to put silicone in the middle and our oxygen's here. Again, it doesn't matter if you put that oxygen like that or if you put it like this. It doesn't really matter. It can go in any, come on, pen, work for me. It can go anywhere. All right. Total number of valence electrons, we have 4. And then we have 2, right? O2. So 2 times 6 is 12. That gives us a total of 16. Again, an even number. So let's go ahead and count here. I've got 2, 4, 6, 8, 10, 12, 14, 16. And I got to stop because that's how many I got. So I got all the valence electrons on there. Let's see if everybody's full. This oxygen is full. Okay, 2, 4, 6, 8. It's good. This is full, but silicone is not full. If you take a look at silicone, right, if we can circle out everything that's attached to it, it's got 2, 4. That's it. It's got 4. So we have to get 2 more pairs, which means we're going to have to add 2 more bonds to fill up silicone. Now, this is a little bit of a trick here. Where do those bonds come from? Well, our first one can come from either place. So let's see here. Let's go ahead and we'll pair off of this one and move it into a double bond, right? That brought silicone up to 6, but it needs to be to 8. So now what do we do? Option A, we make a triple bond here, or option B, we add a double bond here. And the answer is B. We want to do a double bond. A single bond and a triple bond in a molecule like this. Think of nature like symmetry. Okay, if we can do 2 double bonds and it's acceptable, then let's do that instead of a single and a triple. So I'm going to take a pair of electrons off that oxygen and say, no, dude, you got to share. Okay, you got to share with the silicone so it's happy. And now we have our correct Lewis structure. All right. Now, if we count silicone's electrons here, right, 2, 4, 6, 8. So now it's full. That's the Lewis structure for silicon dioxide. All right. Okay, cruising along here. Let's do a couple more. We're not going to do the challenge problem. It's not something that you guys really need to know, so we're not going to do that one. All right, P2. This is phosphorus. Phosphorus, again, we only have 2 atoms bonded together, and so we don't need to find a central atom. We can just do this, get us started. How many valence electrons do we have? Each phosphorus has 5. 5 times 2 is 10. All right. Now, let's put on the rest of the electrons. So I've got 2 in the bond here, 2, 4, 6, 8, 10. So this phosphorus is not full right now. We need to add, it has 2, 4. We need to add 2 more bonds to it. And they're going to come by taking a pair away from the guy that's full here, take a pair off, move it into a bond. That brought the left phosphorus up to 6. And then we're going to take another pair off of here and do this. And that'll bring it up to 8. Okay, so now if we count them, all right, this phosphorus has 2, 4, 6 in the bonds, and then 8 there. And then this phosphorus has 2, 4, 6, 8. So they're both full. So this is called a triple covalent bond. That's a pretty strong bond in terms of bonds. All right. Sulfur. Sorry, we're going to see 3 sulfurs bonded together for our next one here. Now, again, this is one where how do we determine the central atom? Well, we've got 3 sulfurs, so we're just going to go ahead and put one in the middle and attach the other 2 to it. Okay. Now, some people in this and in ozone in O3, they like to make this ring structure. That's a no-no. We're not doing a ring structure. So no rings on any of the molecules that we draw for our class. If you get into higher level biology classes and stuff, then you're going to have some rings whenever you've got 5 chains of 5, chains of 6 and higher. Then we can get rings. But 3 and 4 ring chains, they're not very stable. So we're not going to see that happening. All right, so sulfur has 6. 6 times 3, 3 is 18. All right, and we're going to go ahead and place those on here. So draw red. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Now let me make one more comment here. Some people wonder, why do you always put the extra pairs of electrons on the outside and then do the inside? You can do it the other way. For example, okay, let's say, let me just show you. You can do it the other way here. Erase these dots. Let's say instead of doing, 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm just kind of jumping around a little bit. You know, we can still do the same thing here. This one's full. This one's full. This one is not. And so we're going to take a pair from the one that's full, the neighbor that's full, and we're going to make it into a double bond. Okay. But the way that I would do it, I always fill up the peripheral, the ones that are on the outside, those atoms first, and then I come back in and fill up the central atom. That's just a technique. You figure out what works for you. There's no right way to do it there. So again, 2, 4, 6, 8, 10, 12, 14, 16, 18. And I can see that this guy's not full because it only has 2, 4, 6. So when I take, it doesn't matter which neighbor we pull those from because both of them are full. It doesn't matter which one. So I messed up that one. So I'll just pull this one over and make a double bond. And we get the same structure there. Okay. Right. So I hope this helps a little bit drawing Lewis structures. Again, our rules are really critical to follow. So if you just remember these things, that we always need to have the total number of valence electrons correct. Each atom needs to have 8 valence electrons, but 2 for hydrogen. Have the correct central atom. And then remember, we're never ever going to have individual electrons. They're always going to be in pairs or bonds in the final structure. Okay. I think that's all I have for you guys. Thanks for listening. And if you have questions, always ask because that's a good thing. Sco Ridge.